Hi. In this video, we're going to talk about a couple of ways that we can evaluate limits. There are three methods that we can use to evaluate a limit. We can use a graphical method, we can use a tabular method or numerical method, and then we can use an algebraic method. Those are the three types that we're going to be looking at and the three types that we need to know how to do. In this video, we're only going to focus on two of those. We're going to look at the graphical method and then we're going to look at the tabular method or numerical method. So the first thing that we're going to look at is the graphical method. I've drawn a sketch of a piecewise function up here. We don't have the actual name of the function, but we do have a picture of what the function looks like. And we're going to use the graph of this function to see if we can answer some questions about the limit of this function as x approaches particular values. And I've chosen some values over here that we're going to look at. And the first one that we're going to look at is we want to look at what happens with the limit as x approaches 1, and notice the negative sign up here. That means I'm only interested in what's happening as x approaches -1 from the left. Okay, so I'm going to take my finger and I'm going to run, here's x equals -1 right here. I'm going to find the function to the left of that function. I'm just going to kind of trace my finger, and I can tell that the closer x gets to -1, the closer the function value is getting to 5. Now, I don't care that this is an open circle here. Remember, in our last video, we talked about the fact that we don't care what happens at the value, at x equals -1 in this case. I only care what's happening around it. And since I'm only interested in what's happening to the left of -1, I'm actually only interested in what's happening immediately to the left of -1 here. And as I follow this function around, I can see that the closer x gets to -1 from the left, the closer the function value is getting to 5. And so the limit as x approaches -1 from the left is going to be 5. The next piece asks me to find the limit as x approaches -1 from the right. So very similar here. We're not going to worry about what happens at -1, but this time we're going to kind of follow our function as x approaches -1 from the right-hand side. And as I approach -1 from the right-hand side, I can see that the function is getting closer and closer to -4. And so that's going to be the value of the limit as x approaches -1 from the right. It's going to be -4. My next question asks me, what's the value of the limit as x approaches -1? And there's no sign there to tell me to look for either from the left or the right. And so what that means is that they want to know the two-sided limit. Is x approaching the same thing from both sides? And in this case, since we've already evaluated from the left and we've already evaluated from the right, this is relatively easy to do. All I have to do is look at this and say, okay, in order for this two-sided limit to exist, then the one-sided limits have to be approaching the same value. I have to be getting close to the same number from both the left and the right. And in this case, I'm not. I'm approaching 5 from the left and I'm approaching -4 from the right. And that means that the limit as x approaches -1 as a two-sided limit does not exist. That limit does not exist. So we'll just put D and E. And then finally, notice here that I've also put in f of -1. I put that in there because f of -1 actually, if I look at my graph here, I have a point at -1, -2, so f of -1 is -2. That doesn't have anything to do with the limit at all. I don't care what happens at the value of the function with regard to the limits themselves. Okay, so that's the process of what we're going to be looking at here. The next one that we want to look at is what's happening at 6 from the left and from the right. And so again, here's x equals 6, so we're going to, the first one asked me to look at what's happening at 6 from the left-hand side. And so we're going to follow the function all the way down as x gets closer and closer to 6. The function value gets closer and closer to 1. And so the limit as x approaches 6 from the left is going to be 1. And now we need to look at the limit as x approaches 6 from the right. And so I take my finger and I follow it along, approaching 6 from the right-hand side, and sure enough, it's getting closer and closer to 1. So the limit as x approaches 6 from the left is 1, the limit as x approaches 6 from the right is 1, and it's also true, now that I can see both of those, I can evaluate the limit as x approaches 6. Since the limit as x approaches 6 from the left and from the right is both 1, then the two-sided limit does exist, and it's equal to the value of those one-sided limits. So the limit as x approaches 6, the two-sided limit, is going to be 1. And again, we've got f of 6 here, and if we look at that, f of 6 is actually 5, but that doesn't have anything to do with whether or not the limit exists. Some students get confused and think that if the two-sided limit exists, that means that the function is continuous. But we can see clearly here that the limit exists at x equals 1, but there's a hole in the graph there. And so the value of the function is causing this to be discontinuous. We'll talk about continuity in a little more in depth at a later date, but for right now, what we really need to look at is what the value of the limit is, which doesn't have anything to do with the value of the function. So if you want to take a second, we've got another place here where we could look at this and see what's happening. If you want to look at what's happening to the limit as x approaches -3 from the left and as x approaches -3 from the right, and then look at the two-sided limit and see if what x is approaching from a two-sided limit perspective as x approaches -3. If you'd like to pause the video for a second and figure that out, I'll step away so you can see the graph, come right back in, and we'll talk about that real quick. Okay, so hopefully you had a chance to pause the video, take a look at that, and see what you could come up with. The limit as x approaches -3 from the left, we're following this function here, and we should have seen that as x approaches -3 from the left-hand side, the value of the function was getting closer to -1. So we should have found that the limit as x approaches -3 from the left is -1. From the right-hand side, if I'm approaching -3, the function value is getting closer and closer to +1. So the limit as x approaches -3 from the right is going to be +1. Since those two values are not the same, then the limit as x approaches -3, the two-sided limit, does not exist. So hopefully that's what you came up with when you were looking at this. Now there's a couple of other things that I want to look at with this graph. We're going to look at these a little more in depth when we start talking about limits involving infinity, but I put a couple of these on here just so you could kind of see what was going to happen when we do look at limits involving infinity. And in particular, I want to look at what's happening as x approaches -5 from the right. Okay, so if we look over here at our graph, if we're approaching -5 from the right-hand side, we can see that we're approaching a vertical asymptote here. And the closer the x value gets to -5, the further down this goes. Now there's a couple of ways of thinking here. I've seen this presented as two possible solutions. Some people will say that that means that the limit as x approaches -5 from the right is -infinity. Some people will not necessarily disagree with that, but what they'll say instead is that a limit should be a numerical value, and since -infinity is not a numerical value, we're not approaching a specific value, then we could also say that this limit does not exist. Either one of those answers is generally acceptable. So if you run across something like this on some kind of exam, look for either the -infinity or the does not exist. Either one of those is going to be a possible solution here. The other one I wanted to look at is what's happening as x approaches infinity. So as x gets larger and larger here, we can see that the function is decreasing and it's getting closer and closer to the x-axis. And what that means is that the y value, or the function value, is approaching 0. The farther out I go, the closer that function is going to get to 0 because I'm approaching a horizontal asymptote. So the limit as x approaches infinity is going to be equal to 0. So that's kind of a graphical representation of what's happening with these functions. Oftentimes this is not the best way to approach limits. Usually you would only want to approach this if you have a function very much like this where you're given a graph and you have to kind of piece together what's happening from the left and the right. But this is not the best way to evaluate a limit, but it is a method that we can use. Okay? So now that we have that out of the way, let's talk a little bit about how to evaluate a function using a tabular method or a numerical method. This one is it's not really tedious, it's just more time consuming. And it's not terribly fun to do, and honestly not terribly interesting because you're just looking at a calculator and kind of determining where things are going. But there are some times where this is actually really useful. And a good example of this is the function, the limit as x approaches 0 of sine of x over x. This is a function that's kind of odd to do because if I plug in 0 for x, I get 0 over 0, which is an indeterminate form. It's not undefined, it's indeterminate. And so this may actually have a limit, but there's no way to really evaluate this and simplify it so that we can determine what the value of that limit is. Now, there is a way that we can do it. We don't have that tool in our toolbox just yet. We're going to be talking about something called L'Hopital's rule as we move through the course. And we can use L'Hopital's rule here to actually figure out algebraically what the value of this limit is. But for now, since we don't really know how to use L'Hopital's rule, we're going to go to our calculator and we're going to look at what's happening with the function. So I'm going to grab my calculator real quick and I'm going to put that function in my y equals. Okay, so I'm going to go to my y equals. I'm going to put in sine of x over x, making sure I close that parentheses. And I don't really care what the graph of this looks like because I'm not interested in graphical representation. I want to know what's happening numerically close to x. And so what I'm going to do, once I've got the value of the function in y1, what I'm going to do is I'm going to go to second. I'm using a TI-84 plus silver edition. If this is the calculator you have, these are the steps you would follow. I'm going to go to second window, which is your table set feature. And when you get that, what it's going to ask you is it's going to ask you several questions. First of all, it wants to know where you want to start the table. And I'm going to start the table at 0 because that's the point that I'm interested in. So I'm going to do my table start at 0. And then it's got delta table. Delta table means how frequently do you want to know answers to this? Well, I need to look at what's happening really close to 0, and so I'm going to tell it to look at what's happening at a change of 0.01. So it's going to show me results at 0.01, 0.02, 0.03, and so forth. If I wanted to look closer to 0, I could go 0.001, 0.00001. I can make this as small as I want to try and get as close as I can to what this actual function is approaching as x goes to 0. And it's got an independent and dependent. I'm going to leave both of those set to auto. And then once I have those two things set up in there, I'm going to go in and I'm going to choose second graph. And what this does, instead of bringing up the graph, it brings up the actual table of values. And I'm going to scroll up a little bit because I want to see what's happening not only to the right of 0, because when I plugged in a table started at 0, it started at 0 and gave me 0.01, 0.02, and 0.03. But I want to see what's happening on the negative side as well. And if I do that, what this is giving me is at an x value of negative 0.03, negative 0.02, negative 0.01, 0, 0.01, 0.02, and 0.03. Those are the values that I'm going to use. And I'm going to look at the function value at those points. And the function value for negative 0.03 was 0.99985. At negative 0.02 it was 0.99993. And at negative 0.1 it was 0.99998. At 0, I got an error, which doesn't surprise me because I knew that it wasn't going to evaluate this thing at 0 anyway. Okay, and then it actually turns out that this one is symmetrical, and so the 0.01, 0.02, and 0.03 are the same as their opposites were. And so I'm just going to plug those in here real quick, and then we're going to look at this table of data and see if we can figure out what this function is approaching. And sure enough, it looks like the closer I get to 0, the closer the function value is getting to 1. So I'm going to take a guess and say that the limit of this is equal to 1. Now, like I said, we can look at this later and actually show that that is a correct guess. This is the problem really with the tabular method, though. We can't actually say for sure that that's what the value of this limit is because I have no idea what's happening between negative 0.01 and 0 and positive 0.01 and 0. I don't know what's happening here. Maybe the function went crazy in there. So I'm really kind of guessing that it's not doing that. Hopefully it's not, and my guess is going to be accurate. In this case it is. So that's the way to look at the tabular method for this Not the best method, but we use this mostly when we've got a function that we can't work through algebraically, and we're not going to be able to look at it graphically. This is almost kind of a last resort, last ditch effort to try and find the value of the limit. Certainly not the best method to use. Okay, so that's a look at the two of the three types of finding limits that we have in this in this course. We're going to look at the algebraic method for solving limits, by far the best method to use. We're going to look at that in our next video, where we'll spend a lot more time dealing with how to actually find the value of the limit in a more detailed way. Thanks.